Welcome back. In our last video, we explored a little bit of our data looking at horsepower predicting fuel efficiency. We ran a regression model, examined descriptive statistics, the correlation, and examined our outcomes. So now I've just taken, from SPSS, I've taken these tables, descriptives, correlations, and all the way through our coefficients and move them over into Excel just so we can see some basic calculations. So first, in Excel, let me readjust this. It's more visible. We can see that I've just transferred this over. We have 0.61, we have 0.374 for R squared. We have our analysis of variance table and our coefficients. A couple things to start pointing out. We see our correlation of negative 0.611. That is our standardized beta coefficient. So for horsepower, if we were to standardize our values and use horsepower, standardized horsepower predicting standardized outcome of miles per gallon, fuel efficiency, we would end up with the same correlation. So in a simple correlation, that's the case. We know from class that we get more complex and we have to do some other additional calculations to get our standardized coefficients for multiple regression models. But we could see, if we wanted to look at the unstandardized coefficient here, we could use equations that we've used in class. I'll just sort of quickly show you those. Here's our slope and our intercept. We can calculate slope and intercept in Excel. So I can take my R value, which is negative 0.6, and multiply that by rise over run. We have fuel efficiency divided by horsepower, and we get our value of negative 0.0459, essentially the same thing as negative 0.046, just rounded to a different decimal place. And then if we wanted to, we could also calculate out intercept. We could take our mean of y and subtract the mean of x times our new slope, our standardized slope. So we get 32.37, and now we've calculated it out, the intercept. I won't do this for all of our models. I just thought it might be useful for you all to see this kind of calculated out. So in multiple regression, it'll be a little more complicated. You'll just follow the equations, but you can calculate out both standardized and unstandardized values as well. Our analysis of variance, we've talked through class. This is just like your standard analysis of variance table that we worked with in your previous coursework. For those of you that had analysis of variance or your previous stats course, we have our analysis of variance table. We have our regression, which is effectively our effect, our residual, which is our error. And if we follow forward, we see that 1049 divided by 1 is 1049. And we can see that 1757 divided by 152, well, let's go ahead and do that one. 1757 divided by 152 equals 11.56, just like we have here. We also talked about in lecture that the mean squares, we can think about these as our variance components. These are actually like variances. This is our variance of our effect, our regression, and this is our variance of our residuals. And we know if we take those variances and do a variance of our effect, of regression, over variance of error, our residual, we calculate out our F value. So now we've recalculated out our F value. We also have some of our other values that we would like to calculate out. We're going to examine R squared and R. So first, very simply, R squared, not surprising, is negative, as a regular 0.61. It's always going to be, in this case, in a positive, reported over here. But we know in a simple regression model, R squared, one of the ways we can acquire R squared, is we can see that R squared is only going to be affected by our correlation, which is also our standardized beta coefficient. So if we take that value and we square that value, if we square that value, I just took off it was a character as opposed to a numeric value, we see that we get that 0.373, which is just a rounding error here. So we can actually just calculate r squared out that way. Now, if we don't happen to have, for some reason, the correlation, or if we're doing this in a more complex multiple regression model, we can go to our sums of squares tables. We learned in our r squared is also a function of our sums of squares regression. We can divide that by our sums of squares total, and we see that we get the same value. So there's several ways we can calculate our r squared. There's other methods as well. And for multiple correlation, of course, this is going to be a little bit more complicated, but it's useful to maybe guiding to help you think about these in a simple correlation model first. And finally, just so we can see adjusted r squared, I'll flip back to our equations. This equation is, we can simplify this a little bit when we do this in Excel, and this will be true of your multiple regression as well. We can take 1 minus, so it's 1 minus r squared, which is one way of saying it's 1 minus everything that's not r squared. We can multiply that by that equation for n, and m is really just m minus 1, which is your total degrees of freedom, divided by n minus m minus 1, which is your residual degrees of freedom. And we calculate that out, and we end up with 0.3697, which we see over here is basically the same thing. What we see in the square here is 0.37 is effectively just rounding error. We've calculated out adjusted r squared. And you all have calculated out the standard error of estimate in class. We'll look at predictions and get a little bit more complicated in our regression models in the next video.